And now we need to figure out the dot product of A with itself. So whereas A again is 3, 4, negative 4, so we're going to have 3 times 3 plus negative 4 times negative 4, because that's what you get if you take the dot product of this vector with itself. Okay, so 3 times 3 is 9. This is going to be 16, so you've got 9 plus 16, which is 25. So let's carry on this thread above to work out the rest of W1. So this fraction turns into negative 16 over 25, and then the vector A was 3, negative 4, so here we go, 3, negative 4. And just like last time, it's going to help because, well, after we figure out W1, we need to calculate W2, right? That's the next thing we need to do. We just found W1, we're going to need to figure out W2. So it's going to help to not have this scalar multiple out in front. So it's going to, let's just multiply it into the vector. So 3 times 16 is 48. So this is going to be negative 48 over 25. And then 4 times 16 is 64. So they're both negative. This negative 16, negative 4, so we're going to get positive 64 divided by 25. So that's what we end up getting for W1. And then now we can go ahead and calculate W2. So let's do that. W2 is going to be, remember, I'll just quick reminder, it's going to be U minus W1. So that's what we're going to do here. We're going to go U minus W1. Now U was, again, it just 0, 4. So it's going to be 0, 4 minus W1. So it's going to be minus negative 48 over 25, 64 over 25. And it helps to actually write this as a fraction so it has a denominator of 25 as well. So let's go ahead and on our next line, we will, or next step, we'll go 0, 100 over 25, and then minus negative 48 over 25, and 64 over 25. Okay, so what's this going to work out to be? I'll subtract the first coordinates. 0 minus negative 48 over 25. Well, that's going to be just 0 plus 48 over 25, which works out to be this, 48 over 25, right? Then our second coordinate, 100 over 25 minus 64 over 25, that's going to give us 36 over 25. So that is our vector W2, which is good because that's what we need. The distance between our point and our line is given by the norm of W2. So we need to calculate the norm of W2 and then we are done. So let's do that now. So the norm, this is step 5, I guess. So if I'm being consistent, I'll number it. The norm of W2 is what we want. So we want actually the norm, and I'm going to draw this a little bit bigger so I can actually plug this whole vector in. I'm not going to dive into using the formula just yet because it turns out there's something we can do to just save a couple minutes. So I'm just going to write exactly what we're calculating, right? I just rewrote this, but instead of writing W2, I just wrote the actual vector because this is W2. Okay, now I could just go the square root of this number squared plus this number squared, but that's going to be that's a fraction with a fairly large numerator and denominator, and then you're going to square those fractions. Things are going to blow up, and it's going to get more complex than it needs to be. Notice that we have a common factor here between these coordinates of, they both have the denominator 25. So watch what happens if we just go 1 over 25 times the vector 48, 36. Now this vector only has whole number coordinates. So that's going to be nicer to calculate the norm of. And remember, if you have a scalar multiple, you can pull the scalar right out of the norm. You just have to remember to put an absolute value sign on it. So if I'm really being careful here, I'm going to say the absolute value of 1 over 25 multiplied by the norm of the vector 48, 36. And you're probably already kind of maybe looking at this and saying, well, 1 over 25 is positive. So what are those absolute value bars doing? Nothing, right? So we can just drop them on the next step. I'm going to work to the right so I can have room for the answer down here. So this will just be 1 over 25. And then we can calculate the norm of this vector. And it's only got whole number coordinates. It's a little bit easier than working with this one directly. And it's going to give us the same result because we're taking advantage of the fact that norms are positively homogeneous. You can pull out scalar multiples at the cost of an absolute value sign. Okay, so let's calculate the norm of this vector and then we're done. So we want the square root of 48 squared plus 36 squared. Now, I don't think anyone really is leaping at the opportunity to try to do this in their head. If you can do this in your head, great, good for you. If you want to do it by hand, you want to multiply 48 by 48 out longhand, and then do the same thing for 36, and then see if the result is something that you can reduce as a square root. Again, go ahead if you have the time, but there's nothing wrong with just using your calculator to work out 48 squared plus 36 squared and plug it into the square root and see if you get something nice. And it turns out 48 squared plus 36 squared ends up being a perfect square, which is nice, but in general it might not be. So don't feel bad. If you want to use your calculator for an expression like this, there's nothing wrong with doing that. But what you end up getting is 1 over 25 times the square root of 3600, and like I said, it's a perfect square. Actually, it ends up being 60 times 60 is 3600. So this is the square root of 60 squared. So you end up getting 60 over 25 because that's what the square root of 3600 is. It's 60, and then that 1 over 25, you can just tuck the 25 in as a denominator, and this actually reduces. They have a common factor of 5, so you can write this as 12 over 5. I just have enough room to write that in at the end. So that, finally, is our distance between the point P, our point P here, given as negative 1, 4, and this line L, given by this equation. The distance between them, without having to draw the picture, we could calculate it, and we get 12/5. So finally, we can summarize our answer. The distance between P and L is 12 over 5. So that is our final answer for this question. So that's an example, a concrete example of projections in action and what they give you.